Hello everyone, my name is Hafiz Syahman. Today, we are going to discuss about the Runge-Kutta method, specifically with explaining on the past year question of MSG489 courses 2. This discussion have two session, first by me and next is by Sir Amin Shawqi. Runge-Kutta is one of the most accurate numericals method to approximate solutions of first-order differential equations with given initials value. Most of Runge-Kutta method used fourth-order Runge-Kutta method to obtain best accuracy to find y solutions. This method is a generalization of Euler formula which function f replaced with weighted average of slopes over x interval. This is the first equation of y at n plus 1 th time after function f replaced with weighted average over x interval. By this equation, Euler method was known as first-order Runge-Kutta method when m1 equals 1, w1 equals 1 and k1 is function of f at nth time of x and y. Now, to obtain second-order Runge-Kutta method, we would started from previous equation which gives an algebraic system of three equations as below. There exist four unknowns which is w1, w2, alpha and beta. By solving simultaneous equation, we obtained w2 equals 1/2, w1 equals 1/2, alpha equals 1 and beta equals 1. This would get second-order Runge-Kutta equation as below. Sum of any weighted values must be equals to 1 to obtain each unknown w. For the fourth order, same application applied as second-order Runge-Kutta. Fourth-order method consists of new parameter of unknowns as below. Then, finding all unknowns value to get complete formula of fourth order. This is the formula of fourth-order Runge-Kutta method. Now, we will be going to the past year question section. This section consists of 5 different Runge-Kutta method question. I will be teaching everyone first 2 question, then another 3 question by Sir Amin Shawqi on every Runge-Kutta step. Then, let's start the discussion, shall we? This is the first question, given y prime equals negative tan y and also step length h equals 0.2. Based on the first equation, we need to approximate y solution when x equals 0.4 by Adam-Bashford predictor method. So, we need to apply third-order Runge-Kutta method to find another new initial condition y equals 1 when x equals 0.4. This question tells us about application of two numerical method to find y when x equals 0.4. We go to the solution 1. As per question ask, we should apply third-order Runge-Kutta method where this method tells us to find k1, k2 and k3 by using the equation given by question. Then, we can find the y1 when x equals 0.2. As the result below, solution of y1 when x equals 0.2 is 0.75923. This solution will be useful as another new initial condition to be used for Adam-Bashford method. Then, we may start to compute solution of y2 when x equals 0.4. Given by second order of Adam-Bashford predictor below, we calculate solution y2 predictor with using y1 equals 0.75923 and x1 equals 0.2 to first compute function of x1 and y1, and function of x0 and y0. Then, this 2 function and y1 are substituted in the Adam-Bashford equation to compute y2. Then, as a result below, we get that when x equals 0.4, Adam-Bashford predictor method give us solution, y2 equals 0.63027. We may get a better result if we compute Adam-Moulton corrector method. However, the discussion here prioritize on the use of Runge-Kutta mod on numerical calculation only. Next is question 2. Given that the general equation of fourth-order Runge-Kutta in the new form below. This question asked to find the values of constant, totally 12 constants such as a1, a2, a3 and other 8 constants. This question might be tricky, but the strategy to solve this problem is just do a rewriting a common fourth-order formula, expanding it with k1, k2, k3 and k4, then lastly compare between the equation. Let us go to the solution, shall we? For the first step, we do a rewriting common formula of fourth-order Runge-Kutta method. Rewrite the formula which including the ks part as below. Then, substitute k1, k2, k3 and k4 in the equation w of iteration I plus 1 which all ks formula were given here. Then, try to expand the equation of W until no K4, K3, K2 showed and K1 was displayed as function of Ti and Wi. Then, we already get the expanded equation of W, which we may see that the formula of K1, K2, K3 and K4 were converted to function of f. Last but not least, do a comparison between expanded equation W with equation given by the question. After some observation between two sides, we may identify all constants value, which we can answer the question given. Below here is a result from the observation on both sides.
For question 3, we will use step length of 0.1. Initial value of x is 0 and initial value of y is -1 to find y when x is equal to 0.5. We are given that the initial value of x is 0 and the step length is 0.1 and we need to find y for when x is 0.5. From there, we know that we need 5 steps of calculation. We will use the x is equal to 0 and y is equal to -1 for step 1 to get the value of y1. For step 2, after obtaining the value of y1, we can use it with the value of x1 which is 0.1 to find y2. The whole solution can be summarized as below. Like I mentioned previously, we will have 5 steps of calculation and at each solution, we use different value of x and y accordingly until we reach the 5th step, which is the last step. We get the value of y when x is equal to 0.5 is -0.8196. For question 4, given the step length is 0.1 and initial value of x is 1 and initial value of y is 0. We have to find y when x is equal to 1.4. For the solution, we know that there are 4 steps involved in this question since the step length is 0.1 and initial value of x is 1. We start with x is equal to 1 and y is equal to 0. Using the formula Runge-Kutta 4RD order, we would find the value of K1 and proceed until we reach K4. Once we get to K4, we will use it to find y1. For step 2, it is the same procedure, but this time we use different value of x, 1.1 and different value of y, 0.1052 until we get y2. To summarize the solution. After counting step 1 up until step 4 with different value of x and y accordingly to each steps, we get the value of y is 0.4897 when x is equal to 1.4. For question 5. Given step length is 0.1 and dy over dx is y plus x. Initial value of x is 0 and initial value of y is 1. Since the initial value of x is 0 and the step length is 0.1, there are 5 steps required to complete this computation. After we are done with the computation, we find y5 using the multi-step method. The value of step length, x, and y are the same. Compare the result with the y5 we get using Runge-Kutta. For the solution, we will start with step 1. First, we have to find the value of K1, K2 until K4. Value of k's then would be used to find y1, which is 1.1103. We proceed with step 2 in order to find y2. We will use 0.1 as the value of x, and 1.1103 as the value of y this time. We will repeat this for step 3 until we get to step 5 and we stop as the value of y is already obtained. Next, we will find the value of y5 with multi-step method. Value of y3, f5, f4, f3, and step length, h, are the same as the one we use in Runge-Kutta. Using the multi-step method, we would get the value of y5 is 1.7974, which is the same as the one we find using Runge-Kutta 4th order method. To summarize the solution, When we use Runge-Kutta fourth-order method to find y when x is equal to 0.5. There are 5 steps involved in the computation. And each step has increasing value of y's. We get the value of our y5 at 1.7974 when x is equal to 0.5. On the other hand, when we use a multi-step method just to compute the value of y when x is equal to 0.5, we also get the same value as the one we find in Runge-Kutta, which is 1.7974. The values that involve in the computation of multi-step method are the same with Runge-Kutta method.
That's all from me, Hafiz, and my partner, Amin. Thank you for listening to our discussion, and we hope that we may meet you guys again in near future. Bye bye.